First of all, we'll take a look at disembodied property lists. And the name sounds kind of strange, but what it essentially means is normally we see a property list associated with an object. We query an object and we get a list of properties. Disembodied means it's not connected to an object. It's just a data structure we're going to use within our program to organize our data. So it's logically equivalent to a record. There's basically slots and values, or name-value pairs. A disembodied property list always starts with any value, which is typically nil, and we'll be using that in the course here, followed by alternating name-value pairs. So in the example we have here, we're going to declare a disembodied property list to be a card equal to single quote, and then the list starts with nil, and then we have name value, name value. So the name is rank, the value is ace, and then the name of the next slot is suit, and the value is spades. So this list here, given what we know about lists, we might use like an nth operator or a car and a CDR to move around in the list and find things. But because of this structure, we can use a much simpler and more effective way, which is to use the straight arrow operator to retrieve a value for a given name. So here, for example, we have a card. We can say a card arrow rank, and it will return to us the value ace. We can also say a card arrow suit, and it will return to us the value spades. So you can see it very easily. We'll look down that list, find the name, and then return the value. Now another thing we can do is we can extend a card to have additional values. In this case, we'll add another value with the name face up. So a card arrow face up equals T has added a name value pair to the list. If we were to look at the list, it would actually have that added to it. Here we'll look at the get and getq functions. So get and getq return the value of a property in a property list, including disembodied property lists, association tables, structures, database objects, and a standard object. Now get has no infix operator. The getq does, and that is the straight arrow. That's what we've seen previously. And so here's some examples. If we have a card structure, disembodied property list defined, and we use getq a card rank, it returns ace. And get is a generalized version of getq, and both arguments are evaluated. So if the slot name is a variable, here we've assigned it to suit, get a card slot name would return spades because both arguments are evaluated with get. Now in addition to disembodied property lists, you can also more formally create a structure. Just like a record, and the defstruct function declares a template. So when you use it, it declares a template that tells what all of the slots are, and it automatically defines a skill creation function for this particular structure. So in this example here, we define a card structure and allocate an instance of card. So we say defstruct, the first input is card. That's the name of the structure. And then we give rank, suit, and face up as the additional slots that will be created. Next, we allocate an instance of the card and store a reference to it in a card. So as we mentioned earlier, whenever we define a structure card, it creates a function for us to actually make an instance of the card, and it's make underscore card is the function we would use. And then we use keyword type parameters to input the values of the different slots in our structure here. So we would say question mark rank is ace, question mark suit is spades. And we would make an instance of this particular structure and assign it to a card. So you can see here that we've populated the card structure with rank and suit. Face up was not supplied a value, so by default it is actually nil. And then the other nice thing about a structure that we can't do with a disembodied property list as well is that we can use the type function to check that we actually have a card structure. And a lot of times this is important because if you're being passed data into your function, a disembodied property list is pretty much just a list. So if someone gave you an incorrect disembodied property list or a wrong list, the best you could do is check for as a list. But with a structure, you can actually say, okay, I know it's a card, therefore I know it has these slots in it, and I can go look for those. So the type checking is important in being able to share data and pass data around within your program. The other thing you do with a structure is you can use the same straight arrow operator that you used with the disembodied property list, and you can access a particular slot. For example, a card arrow rank will return ace, or I can change the rank of a card by just saying a card arrow rank is assigned the value of 8. I can also check for the slots in the structure with a card arrow question mark, and I can use the double question mark to get the names and the values stored in those slots. Just like with a disembodied property list, I can also dynamically add a slot for a specific instance by simply using the straight arrow operator. So here for this instance of a card called a card, I say a card arrow marked equals T, and all of a sudden if I look at that particular card structure, I see all of the standard slots plus the one I just added. Skill provides us a way to create and use arrays. The elements of an array can be of any data type, and in addition, Skill will provide us runtime array bound checking in case we try to access an element outside of the bounds of the array. We then use the declare function to allocate an array of a given size. So in the example here, we'll declare an array called week and give it 7 slots. Now it's actually 0 through 6. It starts with 0. We can, if we do a type check on week, we see it's an array, and there's an array p predicate function which will tell us if week is in fact an array or not. Now in this example here, we're going to populate an array with some values from a list. So first of all, we define the list of days to be the list of symbols Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. Then we're going to set a little counter here, which is the index into the array starting at 0. We're going to say for each day in our list of days, go ahead and into the array place at the index day num the particular symbol for that day. And so we'll go through the loop and populate the array, and you can see below what the populated array would look like with the index on top and the value stored there on the bottom. You can also create two-dimensional arrays in Skill. Here's an example of doing that. We say tr times table is assigned the value of tr2d array 7, 7. So it's a 7 by 7 array, meaning index 0 through 6 in both the I and the j direction. Now, there is no direct declare function for a 2D array, so if you look in the notes, you'll see an example of how to declare a two-dimensional array. And what I would suggest is going forward, if you need to declare a two-dimensional array, just use the code in the notes to do that. Now, once you've declared the array, we'll show you how to populate that array. And in this case, we're going to do 2 loops. The first loop is for I 0 to 6. And then within that loop, we'll do another for j 0 to 6. And you can see the accessing the location within the array uses the square bracket around both the I and the j index. So rather than just like bracket ij, it's actually bracket I bracket and then bracket j bracket. That's the correct syntax to access this table. And then at each location of I and j, we'll store the product of I and j. So in the diagram here, you can actually see what the populated table will look like in memory. And you can also see then, based on the code, how to access the elements of that table. Next, we want to look at association tables. Association table is a collection of key value pairs. and you can use pretty much any skilled data type as keys in the table. You can use integer, string, list, symbol, or database objects. So they can be the key into the table. And then what we would use is the syntax for array access to store and retrieve entries. Now in order to create a table, we saw a little preview of this in the file IO section earlier. We use the make table function. And we provide a table name and then a default entry, meaning if we try to access a key in the table that does not exist, we will get back that default entry. Now by default, the default entry is actually called unbound. But a lot of times we like to set it to nil if we're working with lists, or maybe a numeric value if we're storing numeric values in the table, like 0 or -1, for example. So it's up to you when you create the table. Now just a note here on tables, this is the same idea as a hash table in other languages like Perl or Python. Very powerful, allows you to quickly create and store data. And then also, if you refer back to the file IO section, there's actually a way to easily read in a table of data from an ASCII file, or also write out a table of data that's stored in skill out to an ASCII file. So it has very useful input-output functions, as well as it is very easy to write code with a table data structure. Here are some list-oriented functions that work with tables. So basically an association table is implemented as a hash table. The association table access uses the equal function to compare keys. Now here's several list-oriented functions that you may want to use when you work with tables. The first is a for each function. In an example on the right, you can see basically we can use the for each to go through each key in the table, and then key gets assigned the value of the key, and then my table bracket key bracket will access the value stored at that location. Next would be set of. Set of would allow you to filter and find if what keys are in the table based on your condition. Here in the example, we're just checking for whether we have a key whose value is metal 2, the string metal 2. The length function, if we need to just know how long a table is, say we've collected data into a table, we can just use length. If we need to remove something from a table, there's just a simple function called remove. And then, finally, if you need to just test, say your code has a requirement to have a table passed into it and you want to test if it's really a table, there is a table p function to test if a given object is actually a table. Here's an example of using an association table as a dynamic array. And a dynamic array would be one, for example, where we might have a sparse array, meaning we'd have to declare a very large array to store a few values, most of whose entries are in use, so that would be a waste of space. So a sparse array would be an application for a table that represents a dynamic array, or a multi-dimensional array. So we'll show you the example here of a multi-dimensional array. First of all, we'll just have a procedure called tr2d underscore dynamic array, and in that we will just make a table. And that table then would be returned to us and stored in the variable tr times table. And then following the same loop we saw before for arrays, we will populate that table using I and j as an index and then storing the product there. So you can see here, rather than an array, we just use list ij as the key into our association table. Now here's another example of using a table where we can associate shapes with layer purpose pairs. So we'll build our own table in memory of the data that's typically stored in the design database. What we'll do is create an association table, and the key into the table will be a list composed of the layer name and purpose, so that'll be the key. And then the values stored at that location will be a list of the shapes on that layer purpose pair. So here, for example, we're going to make our table. We're actually going to make the table name from the cell view live name, cell name, and view name using sprintf to create that string. Then we'll call make table, give it the table name with our live cell and view, have the default entry be nil, and we'll assign that to shape table. So you see we've created a table. We don't have any data in it yet, but we've just created it at this point. Closely related to association table are association lists. Again, these are key value pairs. The difference is in the syntax of how we specify them. The first example here is creating an association list, and it's basically a list of sublists. Each sublist is a key value pair. Now we'll use the assoc function to actually look up a key in the association list. So we say assoc b in assoc list, and it returns to us the key value pair. Now it's kind of unique in that when it returns it to us, we're actually getting a pointer to that data in the list, not a copy of it, as we typically do with other list functions. You'll also notice if we look up a key that is not in the list, like assoc d assoc list, we get back nil. Now if we want to actually update the table, there's a function called RPLACA, which will allow us to update the first element of a list, and will then replace the car of the cdr of the association list as shown here. So in this case, first of all, on the inside part, we're going to do the assoc function, assoc b assoc list, that will return to us the B2 position in the original list. The CDR is the second element, which is the number 2. Then RPLACA will replace the number 2 with the last input, which is the string 2. So now if we look at assoc list, we see A1, B2, but instead of the number 2, it's been replaced with the string 2. And then finally, if we look at the last element, C3, that's still the same. But the idea here is this original list was modified. It wasn't copied and then updated. It was actually modified as it is. This is typically called like a destructive function. And there are several functions like this in Skill that allow us to modify an existing list. So in summary, we looked at implementing records in the Skill language with disembodied property lists and skill structures. We looked at skill arrays, both 1 and 2 dimensional arrays. And then we looked at association lists and association tables.